we are welcoming him. He's also the chair or the chair of editorial board of Batteries and Supercaps New Journal. We thank him for that. Thank you for joining us, Jürgen, and the stage is all yours.
Thank you, Malachi, and good morning to all of you. It's my great pleasure and, of course, an honor. Particularly, I, of course, say good morning to all my Israeli friends and cooperation partners. In fact, really a great pleasure and honor. The title of my talk is related to the fact that solid-state batteries are recently, or as many of you will know, experience a strong hype. And I think it's all a big bet, and it's not yet really clear whether solid electrolytes will, in fact, enable better lithium batteries. So I think my talk is meant to try to give a neutral and objective view into the field and to the key challenges. And let me start by asking, what is the benchmark currently for solid-state systems? So we recently published an analysis of solid-state systems where we tried to include all published solid-state batteries where full data sets were given. That means we only included those cells where the authors really reported all the necessary data you need to really analyze energy density and power density. And then the data set is not too big. And what you see is, and this is what has to be really careful with the analysis and these Ragone type charts. I will not go into too many details. We see, of course, what we like to see is high energy density and or high specific energy and specific power. Now, lithium battery cells, of course, are already very good. So this is a full cell with housing, whereas all the solid state data in color, which are colored, represent data on the pure materials basis. And I think the general view is simply there's still a way to go if you compare things carefully. So I think this is our cell here, which is doing reasonably well, and include, for example, recent Samsung data with an anode-free cell where they did not use lithium metal foil as anode, but just a modified copper cell. So this is already very good, but this is still on the materials basis. And so it's not really quite fair to compare that. And it's still at elevated temperatures. So quite a number of the data by Samsung are obtained at elevated temperatures. So this is the elevated temperature graph. This is where all the polymer cells usually are in, and this is the room temperature graph where all the inorganic solid electrolytes are. So by and large, I think the performance of solid-state batteries still needs to be improved to meet lithium-ion batteries. And I think it's very careful, I think it's very important to avoid any, I would say, kind of overselling, which you often see if there is a field experiencing a hype. And I think I like to quote a term which Doran often uses, and that is, there is, of course, lots of noise in the field, and you have to be very careful to identify the real advances. Now, I think just for those who are not so deeply involved with solid electrolytes, I would like briefly to start here by showing a cross-section, a schematic cross-section of the lithium-ion battery with an already very thin separator, which is, of course, then also containing electrolytes in its pores. And if we would just replace the liquid electrolyte, we would not gain too much because the solid electrolyte, of course, always has a higher density. We would gain something if we would replace the graphite electrode or the lithium titanate electrode could replace it by a reversible high-rate lithium metal anode. Then we could obtain really I would say, kind of jump in energy density or capacity and in power density and specific power. Now, what is important is there are, of course, some major differences. There are pros and cons. So what is very good is, of course, that solid electrolytes are single ion conductors. So that is very important. You don't run into concentration polarization issues. Thermodynamics, I think, is very not a big advantage of these solid electrolytes because, as we will see, the best solid electrolytes are not that stable and have relatively narrow windows of stability. Mechanics, I think, is at least a disadvantage of the inorganic solid electrolytes and can be an advantage of polymers. And processing surely will be has to be considered right now still as a disadvantage, because processing is well developed and has made lithium-ion batteries cheaper and cheaper over the last years. And for solid-state batteries, probably new processing technologies have to be developed, or we have to develop solid-state batteries such that we can more or less take over processing technologies from lithium-ion batteries. And just a brief slide on the types of solid electrolytes. I think what is important is today we have solid electrolytes that have lithium-ion conductivities that are higher, in fact, than the than lithium, the liquid electrolytes. So we can achieve with the sulfide electrolytes conductivities of 10 millisiemens per centimeter and more. So the conductivity of solid electrolytes today is not limiting. Of course, polymer electrolytes have not yet reached these high conductivities, nor oxide or phosphate electrolytes. So I think 1 millisiemens per centimeter is probably what, or a few millisiemens per centimeter, what you can reach with phosphates and oxides. Just for those who are familiar with thin film batteries, the LiPon, which is a nitrided lithium phosphate, the classic material for thin film batteries, has a really poor conductivity of only 1 microsiemens per centimeter. So analyzing the conductivity issue, I would say that's not an issue, but we will come back to that in a few minutes to really show the problem is we really need these very high conductivities of the sulfides and thiophosphates. And if you make a simple kinetic analysis or dynamic analysis of what can we get with solid electrolyte, then of course there is no real limitation, serious limitation to approach these high conductivities. What you need is a low activation energy and of course high concentration of lithium ions in the structure and reasonable transport path in the structure. But then it's no problem to approach these 10 millisiemens per centimeter at room temperature for activation energies roughly below 0.3 eV. And with the thiophosphates, you see where lots of work has been done by our Japanese colleagues in the last 1 or 2 decades. The thiophosphates can meet that. Okay, so then let's ask, what are the key challenges in solid-state batteries we have to focus on in order really to make, to bring solid-state batteries to a commercial success? So first of all, we have to deal with the cathode composite. And we will see that the cathode composite, the cathode really is one of the, let's say, limiting issues. We have to guarantee ionic and electronic conduction in the composite. And of course, I think you all are aware of the properties of liquid-containing batteries. So I think this is always a reference. So what I do is always considering the solid-state issues referenced against the liquid state. We will see that, in fact, the best solid electrolytes are not very stable at the cathodes, and there is a CEI formation, and we have to avoid that. Chemomechanics plays an important role because I said that the best electrolytes are more or less ceramics, so we have to look for chemomechanics. I will not speak about heteroionic interface kinetics and SEI formation at the anode side, but I will then move on to a kind of model type study to understand better whether lithium metal anodes really can operate with solid electrolytes. Okay, so let's start with the cathode side. And I think the cathode side, as of course also in liquid-based batteries, is considered as a key issue. And what you see here is results from a model type study with Volkswagen, where Anja Bielefeld did a very nice theoretical study analyzing in principle the impedance of cathode composites, where she took cathode particles, typical spherical particles and solid electrolyte particles, allowed porous space and binder, and she then calculated how high need to be the conductivity of the solid electrolyte in a reasonable cathode composite with a reasonable thickness. So we like to see a cathode with a thickness of 100 micron to have enough cathode capacity. And if we like to see a certain C rate, let's say 1 or 2 C, then we see the color here is then the C rate. The solid electrolyte conductivity that is needed to achieve that has to be already in the order of 10 millisiemens per centimeter and better. So the 10 millisiemens per centimeter are a necessity simply to get enough ionic percolation and enough ionic conductivity, effective ionic conductivity in the cathode composite, and she translated that of course into the tortuosity. Here she assumed a tortuosity factor of 4, and I think this is something which we already demonstrated, that the percolation path in a solid electrolyte are really critical. So what you see here is that we investigated cathode particles. So this is NCM622 cathode particles with different average thickness or diameter from 5 to 8 to 15 micrometer. And whereas, in fact, the ionic percolation is more or less independent of the cathode particle size, electronic percolation, so here is no additive, conducting additive added, the electronic percolation goes down with increasing particle size. So if you only have the same amount of cathode material in your cathode composite with big chunks of cathode particles, then the electronic percolation, of course, goes down. So there is a, I would say, an improvement in electronic percolation going to smaller particles. And what we see, of course, today, there is this trend to small single crystalline particles in solid state batteries, maybe also in batteries with liquid electrolytes, and we see that there is a necessity again also to go to the direction of smaller particles. Just a side comment, together with a group of Wolfgang Zeyer, who is now at Münster, made a very nice study, essentially Georg Ewald did a very nice study of these tortuosity effect in solid state lithium sulfur cells. Now, solid state lithium sulfur cells have a cathode composite of sulfur mixed with a solid electrolyte, which in this case is an agarudite material, and carbon. So this three-phase composite, which of course also still contains some porosity, is being studied in solid state batteries. And what you see here is the tortuosity factor. This is the Bruggemann relation, which simply, which is a relation for describing the tortuosity of spherical particles in a matrix. And you see, which is, so say, a relatively, well, let's say, low tortuosity environment. And you see, if you go to a solid state with a solid electrolyte, the tortuosity becomes much higher. This is for ions and this is for electrons. So the microstructure of the cathode composite with a solid electrolyte is far more critical, I would say, than with a liquid electrolyte, because the liquid electrolyte impregnates the porous structure, has no grain boundaries, no dislocations, is always more or less the same. But if you deal with a solid electrolyte really adds complexity to the microstructure of the cathode composite, and that has to be taken into account. So that is the reason why only the best solid electrolytes with really, I would say, ultra high conductivities can be used in cathode composites. Now, that means, of course, that other electrolytes, phosphates, oxides, can be used as separator electrolytes, where if you have a thin electrolyte, a thin separator electrolyte, the conductivity does not need to be that high. Okay, now an issue is, of course, that if we use now these sulfides and thiophosphates that have really a narrow stability range because they're easily oxidized, they contain sulfur in the oxidation state -2, and that is easily oxidized already at potentials of, let's say, 2.3, 2.5 volts. So always when they are in contact with, direct contact with cathode materials that of course always have a higher potential, they degrade. And what you see here is tough Sims images where the color corresponds in fact to certain species. So this is a mass spectrometric image, and you can also get it in 3D. What you see here, this is the agarudite in the mixture in the cathode composite, pristine after 0 cycles. So the blue color is representing, in fact, the nickel is the NCM materials, and green color is representative for phosphate. Now, a thiophosphate does not contain oxophosphate, but you see, after 100 cycles, there's lots of green color, which means around the blue cathode particles. And that means the sulfide electrode has been oxidized and now forms an oxidized shell with high impedance around the cathode particles. So there is a CI formation, and the CI is, it's in fact has a high impedance here in different color code. You see, again, this is cathode particles. Now the red halo here is indicative of phosphate fragments. So during cycling, the NCM material gives off oxygen, and this oxygen reacts with the thiophosphate electrolyte, oxidizes it, forms phosphate and sulfide, and increases the conductivity. Now, if you have really then a cathode including carbon additive you may protect your cathode particles, but if you use then carbon fibers or whatever carbon conductive additives, they also have the potential of the cathode. And we were able to show by Prof. Simpson XPS that also the electrolyte around the carbon additives is being oxidized, and also at the current collector. So there's lots of degradation going on. This can be really in detail being clarified and analyzed. So we were able to show that, of course, during oxidation, phosphates and sulfides form out of the sulfide electrolytes, and polysulfides that may even in the extreme go to sulfur. And this is interesting. That means that the electrolyte is not only degrading, it adds to the capacity. And I know that some Chinese groups try to use that by using the electrolyte itself as an active material. Okay, now another indicator of the decomposition of the electrolyte is gassing. And what you see here is a pellet type solid state battery. There's a cathode on top. There's a relatively thick solid state separator, which is Li3PS4 in this case. And we use a battery with NCM622. And what you see is here the cycling of the cell, CO2 and O2 come out of the cell. So this is a DEMS measurement. Out of connected porosity of the solid state battery, gases come out. But what we see is there's also some SO2 coming out. So in fact, this is another indicator for the reaction between oxygen from the NCM material with the sulfide electrolyte forming even to gaseous side products. Now, that all means we have to avoid the direct contact of these excellent sulfide electrolytes with the cathode active material. This is, of course, well known from the work by Toyota and others. So coating of cathode materials is a requirement. Otherwise, the impedance will grow, the capacity will fade too much. And there's various concepts. I think the classic is lithium niobate, and in the Bella lab in Karlsruhe, we tried a modified lithium niobate coating. So it's essentially a mixed lithium carbonate, lithium niobate coating. We use the lithium carbonate, which is always after storage on the high nickel materials. And by doing that, we see that the pure pristine material fades in the solid state battery much stronger than the coated cathode materials, where in fact the best results were obtained. This is the red data when we used our mixed lithium carbonate, lithium niobate amorphous coating. If we have this amorphous coating, you see that even then, so this is the red data here in the DEMS data, then there is no SO2 being shown. So in fact, the coating also seemed to really solve that issue of direct reaction between the NCM material and the electrolyte, but not completely. You see there's still fading, and I think there's still work to be done. And I think I also have to conclude that cathode coatings as such are not so well understood. So there is still room for work on cathode electrolytes. Now let me come to chemomechanics. What you see here is the volume change of active materials, of cathode active materials. So lithium cobalt oxide is expanding upon delithiation. So because you remove the Coulomb glue between the oxide layers, well, all the nickel containing materials from NCM, NCA, NCM 811 and so on, they all shrink during delithiation because nickel is being oxidized to the small nickel 4+ ion. That overcompensates the Coulomb effects here between the gallery. The effect, however, is not too big until half delithiation. It's only 1%. But if you calculate then the volume change, it's enough that particles may lose contact and that they crack. This is, of course, well known. This is just another representation of the volume effects by partial molar volume, where you see that in the extreme, the nickel-containing cathode materials really show stronger volume effects upon delithiation in the field of where they are already strongly delithiated than lithium metal, for example. Okay, the effect is, and this is, I think, has been nicely shown by Raimund Körber in our group, that the cathode particles that originally have good contact, so this is a typical secondary cathode particle, they lose contact after cycling. And you need external mechanical pressure to keep contact. Now, what Raimund did, he showed that by mechanical blending, by taking shrinking and expanding NCM and LCO particles, you can mitigate that problem. However, internally, of course, locally, there's still lots of strain. And for example, you see here that this LCO particles really has been strongly strained and deformed under the impact of local strain in these solid state cathode composites. So I think there is probably only two real solutions. And one is you need any kind of mechanical buffer layer around the particles. Maybe the coating has to be a buffer layer, maybe being a polymer, or you need cathode particles that do not show volume changes. And this is shown here. So Florian from the Bella Lab showed that if you go within the NCM family to NCM 271 and NCM 361, these materials, unfortunately being, I would say, high cobalt materials and not high nickel materials, these high cobalt materials, with these concentrations or fractions of the nickel, cobalt, and manganese show virtually zero relative volume change. So I think volume neutral cathode materials can be developed. Of course, the volume change is not isometric, and the A and C axis deform differently. So there is, of course, still local strain, but nevertheless, during cycling, we see that there is virtually no volume change, no pressure coming up in these cells, which is an improvement, however, on the cost of a higher cobalt content. Now, something, and excuse me, something which I think is really nice is something Raphael showed together with Volkswagen recently, and that is a study, a comparative study of the effects of chemomechanical expansion of solid state batteries and liquid based batteries. Let's start with the solid state battery. What you see here is a cartoon of a secondary particle and the solid electrolytes. Now, and if we cycle that, you see here the chemical diffusion coefficient of lithium, the apparent chemical diffusion coefficient, which we measured in GITT measurements. And you see now we charge our solid state battery. Chemical diffusion coefficient is, so to say, increasing as it always increases, goes down at the end when the lithium content is going down, and that this is reversible. So nothing is really changing. Now let's go to a liquid electrolyte based battery. The same cathode, everything is the same, just the liquid electrolyte is being used. Now what happens is we start, of course, at the same chemical diffusion coefficient because it's the same cathode material. Now we charge our liquid based battery, and the chemical diffusion coefficient, interestingly, grows much faster, grows much higher than the solid state battery. How does that come? Well, our NCM material is cracking, and the liquid electrolyte is invading and impregnating into these newly formed pores. And if we go back, then the chemical diffusion coefficient remains high, almost higher by 2 orders of magnitude. So the cracking of the high nickel materials in this sense in the liquid electrolyte is good because it opens up the particles and allows fast rates. Of course, it opens new surfaces that degrade and lead to faster fading, but in principle, the cracking is good. While in the solid electrolyte, I think we open up pores, and the electrolyte, of course, cannot intrude. So I think this, in relation to Jean-Marie's talk, it could mean that, well, this is also space or room for self-healing concepts, or let's say self-modifying concepts to be involved. Okay, and the final minutes I would like to start with the lithium anode, and I think solid electrolytes are often considered to be enablers of the lithium metal anode, and let's see whether this is true. I'm pretty sure that Shirley Meng this afternoon will also comment on that, because he has done recently published some very nice results on amorphous lithium deposits. Now, what we did is we studied the lithium metal deposition and dissolution as a function of pressure. So we have a device where we can control temperature and the pressure, and can measure also the pressure that is being exerted by the cell. And we choose lithium garnet as the model type solid electrolyte, because this is virtually stable against lithium metal. So we wanted to have used an electrolyte that is stable versus lithium metal. All the thiophosphate and sulfide electrolytes form an SEI, which is of course then a side reaction, but we wanted to see an electrolyte that is thermodynamically virtually stable. And what you see here is that the impedance of the electrode interface with increasing force is going down and down. And what Torben quite nicely showed is that if you increase your force orthonormal to the interface, it follows a linear relation as a function of the inverse square root of force, which relates very nicely to the theory of constriction resistances and point contact. So if you have contact just two materials that are rough, then you always have only a few point contacts, and each point contact is a constriction resistance. And if you increase pressure, then of course you increase the contact area, and that lowers the impedance. And what Tom showed, if you increase your pressure and your force to the strong enough, you don't see any more resistance. And this is, I think, quite exciting, because that means that the charge transfer itself does not have really a high impedance or a high resistance. So in the case of in these experiments, he showed that about 4,000 bar, so 4 kilobar, were required really to see a negligible interface resistance. In a few minutes, I will show in a much, I would say, nicer experiment with a single contact how low the interface impedance really can get. Now, the critical issue of the lithium metal anode on a real solid electrolyte that has a certain rigidity is the fact that if you anodize a metal, always unavoidably, this is an inherent step, is you anodize the metal, and by removing a metal atom from the metal into the solid electrolyte, a vacancy is being formed. So stripping metal on a solid electrolyte means you inject vacancies. And then the question is, where do these vacancies go? Are they fast enough to diffuse away? Then your electrode remains stable. But you can estimate this diffusion limiting current density. And we did that with, I would say, quite a number of model assumptions. And then we came to the point that the critical current density below you can stably cycle a lithium metal anode on a solid electrolyte, in this case is what LZO, but I think this is quite representative, is about 0.1 milliamp per square centimeter. So all current densities above 0.1 milliamp per square centimeter of room temperature should lead to inherent unavoidable instabilities of the electrode. Simply by vacancy diffusion or vacancy injection, the vacancies are not removed fast enough from the interface, and then they aggregate and form pores. And what we see is, of course, pore formation and the increase of interface resistance by the loss of contact. So this is, let's say, one important finding. Now, nevertheless, what you can show if you really prepare your electrode nicely by strong pressure, and even if you remove the pressure until sufficiently pores are being formed, I think we were able at room temperature to strip about 6 micrometer of lithium with a current density of 0.1 milliamp per square centimeter. But of course, these 0.1 milliamp per square centimeter still, I would say, by and large, 1 to 2 orders of magnitude too small for practical applications. Because in practical applications, in order to be competitive, we need, of course, current densities in the order of a few milliamp per square centimeter. And this is something which I think is still not, at least to me, not possible. I think there is quite some announcement of QuantumScape. You may know that, but they may have found a solution for an anode-free cell where a lithium metal anode may be cycled well enough at high enough current densities, but I think this is still to be communicated. So the overall picture is, by and large, that at low current densities, we create vacancies by injection. They can diffuse away and our interface remains stable, so we have a constant interface resistance. Now, if we draw a too high current density across the interface, we create pores and the interface resistance is, so to say, is increasing and the interface gets unstable, or we apply strong pressure, get creep and continuously deform our lithium metal anode. And then of course, we also keep the resistance constant. Now, let's come to plating. Now, assume that we have this stripping and we have only a few contact points. Then what happens at these few contact points? Now, this is simulated by a tungsten needle on a solid electrolyte. So this is a single grain of lithium zirconate in a, in a scanning electron microscope. So this is 20 microns. So this is a microelectrode experiment. What you see is we deposit lithium cathodically with increasing voltage. Don't be surprised by these high voltages. These are, of course, the voltages that are so high due to the constriction resistance of this small electrode in this electrolyte. What you see, lithium is growing and growing, and the higher the voltage gets, the faster the lithium grows. Suddenly a new growth mode comes out. So lithium shoots out quite a distance from the electrode. And if you look closer, we see the lithium is spilling out of the electrolyte in the forms of whiskers grown together. And I think what is really exciting is in a second, you see there is lithium really shooting out of the crystal, which is not directly contacted by the electrode. You see lithium wires, single crystal wires shoot out of the solid electrolyte. And if we analyze the rate of growth and the contact area of these whiskers, we see that the current density of this lithium whisker growth on the solid electrolyte is in the order of several amps per square centimeter. So if you have a good contact, the lithium growth is not limiting. But the morphology is critical, of course. And I think, Tom, this is the final experimental slide to be shown, is use that to make another very nice experiment on a single crystalline grain of LiZO in a very, very clean environment. He used a tungsten needle, deposited some lithium before, and then measured the impedance of this single contact. And the result, in fact, is that the areal resistance or the charge transfer resistance of a ultra clean metal solid electrolyte contact is smaller than 0.1 ohm square centimeter. So I think this is exciting on the one hand, because it shows that the electrode as such, the metal transfer, the charge transfer is not limiting. It's the morphological development of these electrodes that is limiting. Okay, with that, I think it's time to conclude. I think, first of all, in order to bring solid-state batteries to success, is we need these solid electrolytes with very high ion conductivity, higher than 10 millisieverts per centimeter. Otherwise, we will not be able to construct competitive cathodes. This does not correspond to the separator. There we can use poorer electrolytes. I think we need processing of cathode composites with high effective conductivities. It's not enough just to take the electrode and say, okay, this has a high conductivity. The effective conductivity has to be high because tortuosity effects may be critical. Chemomechanics has to be overcome, the issues with that. We need protective coatings in order really to keep the sulfide electrolytes, I would say, alive for long enough cycles, high enough cycles. And I think the high rate lithium metal anode is still a challenge, but I will of course be happy to learn whether QuantumScape or Samsung at the end find their ways to anode-free cells. With that, I thank my teams, of course, in Gießen and in Karlsruhe. I'd particularly like to thank Wolfgang Zeyer, who is now at Münster, and Felix Richter, BMBF, for funding our national solid-state battery cluster. And of course, I thank you for your attention. Thank you.
Thank you, Jürgen, for your amazing talk. There are questions in the Q&A. If you can push the button, and there is time.
Yeah, let me see. I have to see. Okay, the first question I see is, what about thickness of solid by Aqib Shamim? What about thickness of solid compared to thickness of several present? Yes, of course. The separator issue is an issue. You have to find ways to create, I would say, large area, 10 micron or even thinner solid electrolyte films without pit holes. I think there are ways by printing technologies, but this is definitely one other challenge to be overcome. Yes, but I think what I know is that the companies working on these, the Solid Power, for example, in the US, I think there is technical ways to prepare separators with these thin thicknesses. But I think it's one, of course, issue. Then I see Florencia Macchini, Collège de France. What is the upper cutoff voltage to use for LCM? Okay, yes. Well, I think the point is, once the sulfur has been oxidized, and it is being oxidized, of course, already at rather low voltages, and then the upper cutoff potential is not so critical. I think we typically go to 4.3 volt, but we even test 4.5 volt. The problem is, of course, that then the oxygen evolution from the cathode materials creates a problem. So we typically go to 4.3 and even up to 4.5 volt. Then next question, Amol from South Korea. Magnesium ion, future of solid state magnesium battery. Okay, well, I would say first the liquid state magnesium battery and then the solid state magnesium battery. That is my my feeling. Now, I think there is reasonable liquid based magnesium electrolytes, but I think all the divalent and higher valent ions are really slow in the solid state. And development of a solid electrolyte that has sufficient conductivity, I think, is here a key issue. So this is really a big thing to be drilled. So how do you measure gas evolution? This is a question by Abigail. How do I measure gas evolution? So this is a standard, I would say, standard DEMS experiment. So a differential electrochemical mass spectrometry experiment, where we have, of course, a specially designed cell to contain our solid state battery under certain pressure, but it's, I would say, not too different from a standard DEMS experiment. Then Tushan, if solid state electrolytes can implement in commercial applications, what would be the maximum thickness? Well, of course, if you're really interested in the detailed numbers, I refer to our paper from the beginning of this year, where the paper by Simon Randau in Nature Energy, where we also supplied all the Excel sheets so that you can make all these calculus yourself. But in principle, these calculations are, of course, something you can do with a pencil on a piece of paper. In order to be competitive, you need, of course, let's first of all, cathode composites with a sufficient cathode loading and thickness to have enough capacity. So you need simply cathode composites or cathodes with a thickness of, let's say, 100 micron or a bit more, with high enough cathode material loading. Otherwise, you lose, of course, your energy density and power density. And the separator, in fact, needs to be thin enough. I think it needs to be as thin as the separators in liquid electrolytes. No big difference. In principle, everything has to be even a bit, I would say, a bit better than a liquid electrolyte battery, because otherwise you will not get better. You will not even beat, I would say, the liquid based battery. Lang Long Wang, I couldn't know about the coating. Okay. Yes. The coating material, in fact, should, of course, have enough ionic mobility or ionic conductivity. Otherwise, it will add to the impedance. And the electronic conductivity, in fact, needs to be lower. And this is something which is very nicely shown in a paper by Takashi Nakamura and us last year. The electronic partial conductivity needs to be lower than the electronic partial conductivity of the solid electrolyte that is being used. So this is an interesting phenomenon which I think is often overlooked. So if your solid electrolyte has really a very low electronic partial conductivity, in order to protect really the electrolyte from the cathode material, your coating material needs to show a lower electronic conductivity than the solid electrolyte, and that can be critical. So the design of the cathode material is something that is so far, I think, would say not. It's probably a bit overlooked, and this is an important issue. I agree. I think your question is really good. I think we
again, rest of the questions we will organize and send you for your consideration via email. I want to thank you again for joining us. Thank you for your talk and time. Highly appreciate it.
Thank you for attending.
Thank you. Yes. So